Okay, kia ora koutou, no mai taute mai. Hello and welcome. I'm Dr. Kate Pedley, so I have to start off apologising because Graham unfortunately wasn't able to make it in the end. So he was going to do the talk on structural geology, but as it turns out, I'm also a structural geologist. So I didn't prepare for this talk, but I'm going to take this opportunity to show you how I've been using Visible Geology to help visualise some of the exercises in my structural geology class at second year. So I'm from the University of Canterbury in Christchurch, New Zealand. And we specialise in engineering geology and earthquake geology. So we do a lot of fault mechanics, folding, all sorts of kind of tectonic-based things, as well as preparing students for the engineering geology sector. So a lot of those kind of type problems. So how many of you have actually played with Visible Geology? I know you have, Myra. Oh yeah, you guys. Have you guys actually played with this program at all much? Okay, so a little bit about it. Well, you may have heard some of the spiel, but two key things. It's free and it's browser-based. So there is no barriers to accessibility. This is really important. You can get your students to just bring a laptop along to class while they're doing your normal exercises. And because it doesn't need special hardware, and you can kind of weave it into your just normal program per se. So I haven't had to do much to bring it into the classroom in terms of weaving it through my already existing exercises. So as you can see here, I've got some examples of just a normal workflow from a series of exercises in the lab that students are working through. So as you can see, just plotting up traditional features. And so the first way that I'm using Visible Geology is just for the students to check that they understand it. So they're doing this by hand on paper, and they're going to be plotting it on the Stereonet. But then they can take what they've done and check it out on Visible Geology and self-check that they've got along the right lines, and also visualize what it actually means. So bringing them back into what it's actually used for in 3D. So if we take an example here, so 025, so the strike of 025, 25 degrees to the southeast. If we go onto Visible Geology and we click on the Stereonet, we can put that in fairly straightforward. So what we're doing here is a plane. So we click on plane. We can give it a title. This is quite good if you want your students to save their work. And particularly they can actually hand these in as examples to show that they also did them to back it up. So we've got 025, 25 southeast. I think that was right, was it? Yeah. Okay, so down here, 025, and the dip is 25. Just note that this program currently doesn't put the 3 digits in, but it is the same thing. And just make sure that it's in the right-hand rule. Otherwise it will give you a different answer. Okay, so you can see there what it would look like for the students when they're plotting up the plane and the pole on a basic Stereonet. And the beauty of this is now they can visualize what that actually represents. So very powerful, because a lot of them particularly don't understand the relationship of the pole to the plane. That's one of the biggest ones they struggle with. So you can get them to really visualize how the Great Circle mimics the actual plane in 3D, and how the pole is at right angles to that and coming out in the opposite quadrant. So it's just a great way of letting the students explore at their own pace how that visually works, and let them get their head around and relate it back, so they can keep, if they click on this one up here, they can go straight back to the plan view and the map view and compare that with what they've got on their paper. And then of course visualize that in the 3D as well. So that's the basic method in terms of one plane at a time. Similar for the lines and stuff as well. What I've found this most useful for is when you're starting to work with more than one plane, and you're asking students to then look at patterns and make some extra inferences about how those relate to each other. So another example I've got here, this is kind of jumping up in level quite a bit, but as an earthquake geologist I do a lot of work with structures in stereonets, particularly faults, and stress directions, so sigma 1, 2 and 3. So I can present these models to students. It's fair to say they struggle to get their heads around it a little bit. And the nice one about this type of model is going back to the book model. I don't know how many of you are familiar with this one, but an open book model, which, bear with me, will be relevant for the stereonet. But the idea that if you've got an open book, open is two conjugate pair of faults. You've got sigma 2 being the spine of the book, okay, and then your sigma 1 going down into the open pages and sigma 3 being at right angles to both of them. So all of those three axes have to be at right angles to each other. So trying to find that relationship on a fault plane in a stereonet can be quite challenging when you can't see in 3D. So you can use that principle though to start to visualize it with visible geology. So if I go to the exercise, for this one in particular, okay, so note this last number 6 down here. So we've got two conjugate pair of fractures, compressive fractures, with two strikes and dips. So we've got those two planes, which we know, so we can plot them in visible geology, and then I want the students to think about where they're going to find the axes, okay, or the lines of intersection between the two planes. So if we go to visible geology, so I'm just going to get rid of this one, and we're going to plot these two planes up. So 0, 4, 1, 61. And we've got 19366. Sorry. Apply. And another plane. So that one was 193. Just double check. Okay, make that blue. Apply. Okay, so you can see the two planes plotted. So this is a pair of conjugate fault structures with two planes intersecting. So if I'm asking my students where are they going to find sigma 1, 2 and 3, they kind of, well, I've been talking about this with a few other people. What you might notice is a lot of the time they're just memorising the steps and they're really not understanding what they're seeing and why, because they're just looking at this 2D view, and it's a little bit meaningless when you strip it back to your great circle and your poles. So with this in 3D, you can now instantly, straight away, see that line of intersection between the two planes very clearly. Okay, and so the students themselves, if they think about starting from sigma 2, which they know is the spine of the book where the two planes intersect, they can see where those two planes intersect in the 3D model visually. So they're not just looking at the pattern on the stereonet, they're actually able to see that line of intersection where the two planes are meeting. So they can see that line there, and they can see how it ends right at the crossover point of those two great circles. So it makes a lot more meaningful to them as to why that is actually working and why that must be sigma 2. They visually can see why that works. So my students have found that really powerful for actually understanding and starting them on what is quite a challenging and difficult problem to get their head around. You can also see then, okay, with the two poles, that your sigma 1 has to be in line with the two poles right through the middle of the two planes. So if you can see it in the in the 3D, it's got to go halfway between the two planes, and it's got to be in line with the poles. This one's a little bit, sometimes they need a bit of help to visualize that, but what it would mean is that then if they draw a great circle connecting those two poles, they'll be able to figure out the midpoint for sigma 1. Okay? So we can actually do that with visible geology as well. We can get them to try and make a great circle. It's a best fit great circle. If I go back to the plan view, if we think about a great circle connecting these two, so these 2 points have to be on a great circle, okay? Then we might think that, you know, they're both along this side of the middle, So we want a sort of an arc that's going to go through both of them. So we can kind of see it's going to have a bend towards the northeast, roughly. And it's going to be striking roughly kind of towards the 300, 310. Okay, so we can put in a plane and we can edit it in real times and change it as we go along. So I can just start with an approximate plane. So I can go, okay, if I try a strike of 310, for example, okay, and a dip, I want to put a bit of a dip on it. See, that's actually not going to work. That's going to be, I can see that already that it's not going to pick up the blue one very well. But as I say, the whole point is you can get them to try and work through it. So if I pick, say, 50 degrees, let's see what happens. Okay, so that's not quite lining up, but that's okay because you can get them to edit it. So you can go back to the edit button and they can see about moving it around until it picks up both of them. So here we can go maybe 295. See what happens when we do that. That's better. Okay, so you can see it's starting to line up and pick up the points. And this we're going to have to make it slightly steeper. So the dip's going to be slightly steeper to come back to make more of a dip down from the outside. So we could try 60. It's pretty good. Okay, it doesn't have to be perfect. But when you go back into 3D, you can then see how it's picking up those two poles, and that plane is intersecting both of them. Okay, you can see how they're lined up on that plane. So the students can now see that this plane is a cross-section line through the perfect middle of those two planes. So they can see here how this is the line of intersection and this bisects it through the middle, even though the whole thing is kind of spun around. So from that, they can then see that the midpoint would be counting along that great circle between those two arcs. So it just helps them visualize how they find those points. And there are, obviously we show them sort of the methods to plot it, but they can actually help visualize how that all works and why it's working. And then sigma 3 has to be 90 degrees away from sigma 1 along the same plane.
So as we all know, atmospheric temperature has increased a lot. Last year it reached almost 1.5 degrees Celsius increase, which is a big...
Really good for rakes as well.
So this is the rating peak course.
So you can do it either manually, so the way I'm doing it with my students.
On Earth's energy budget since 1979 to 2022. Here you can see I can't really use the filter, but this
is with things like this. So they've got a plane and then they've got a trend and plunge of slick sides, and they can work out what the rake angle is quite easily when they plot the two of them together. So again, helps them just visualize it. So if we go back to this and just start that again, just going to delete these. So we can put the plane in. So we've got 0, 4, 5, 60 degrees.
of CO2 over the 100 years. So even though the mole fraction, the concentration of methane is much smaller.
Okay, so there's our plane, which again we can visualize quite nicely in 3D, how that actually looks as a plane in 3D space with its pole. And then we can also plot our line of our slicken sides. So we've got our plunge of 26 degrees towards 061.
Carbon dioxide has increased
So this time we go to the line feature, and our trend is 061, and our plunge is 25 degrees. Okay, so it plots just as a line, but of course we can see that line essentially etched on the fault line. So that's our scratch marks on the fault line, so they can see that visually how that works. And then why the rake is just the angle in there between that line and the strike line of the fault, and they can see how they can count that along the great circle. So when they go back to their stereonet, they can count that along the great circle and they know why they're doing that.
So the fact that methane is actively
So My students have found it very, very useful. It's simple, you don't have to overdo it, but it makes a world of difference in terms of being able to visualise it.
Right now, and we can see the changes in the atmosphere.
Anyway,
30 years.
that's probably it for just a little demonstration. If you've got any questions, just let us know. And these guys are awesome to help out, explore it, and you can try the software out yourself as well and have a play around with it.
This graph
Thank you.
shows